Welcome to another lesson of CS360, and in this lesson we will study how to show that languages are not context-free. So how do we show languages are not context-free? And the answer is we use the pumping lemma, not the pumping lemma we've seen before, but this time what's called the pumping lemma for context-free languages. So this is a different theorem, actually a different lemma. It's called the pumping lemma for context-free languages. Okay. All right. So it's called the pumping lemma just because it's very similar in form, but it's actually a different theorem. Okay. And the idea is so we want to show a language is not context-free, right? So we're going to find a property that only context-free languages satisfy. And then so you just have to show that a language does not have this property, and then you would show that it's not context-free. Okay, so we want a property that all the context-free languages satisfy. Not that only, but rather that all. So a property that all the context-free languages satisfy. And then if you show that a language does not have this property, then it will not be context-free, right? Because all the context-free languages satisfy this property. Okay, good. So what is this property we're going to have? Well, one property is that, every context-free language has a context-free grammar in Chomsky normal form. Okay, we know that. But then it's hard to show that a language does not have a context-free grammar in Chomsky normal form. So let's think further. What are some of the implications of having a grammar in Chomsky normal form? Okay, and one of the implications is that basically for each string in the language, so if A is context-free, A has a grammar in Chomsky normal form. So let's say G is in CNF form, such as Chomsky normal form, and then L of G is A. Okay, so for any string in A, we have a parse tree, and the parse tree, and let's say the string is not empty, so the parse tree is going to look like a binary tree, right? Because our grammar is in Chomsky normal form. So, and then whatever we get something like this. Okay, so the string can be read off of the leaves here, 0, 1, 0, 0. Okay, and one interesting thing to note here is that the characters occur on the leaves, right? And the tree is a binary tree. Each time it splits into 2, except at the leaves. Okay, which means that if our string W is long enough, so let's say W, we know that our grammar has finitely many variables and rules, right? That's part of the definition of a grammar. So let's say let K be the number of variables, right? So this is the size of the set of V of variables in the grammar G. Okay, and then say that W, the length of W, is bigger than n, which is 2 to the k. So define n to be 2 to the k. And then let's suppose that our string is bigger than that. So for a sufficiently long string like this, well, the string is an A, so it has some parse tree. So, okay, so it's a super long string, right? Okay, and it's W, and W is a super long string. Okay, whatever, it's a super long string, and it has some parse tree. And the parse tree is a binary tree, right? Like each time it splits into 2, and it might not be equally deep along all the levels. So at some point it may end early, like this 0 might correspond to that 0 over here. But the sequence of all the leaves in the end corresponds to this giant string. Okay. Now, since this string is length, the length of this string is longer than 2 to the k, and k is the number of variables. So the depth of this tree, in order to generate this giant string, must be at least k. Okay, just because each time we split it to only 2. So the depth of the tree basically needs to be at least log base 2 of the length of W. So it basically needs to be more than k. All right. Now there's only k variables. So because there are only k variables and the depth is basically more than k, then this means, but by depth, I mean the depth of the longest path down. So there will be some long path down where, where down this long path here, let's say this long path that I'm highlighting. So down this long path, the length is going to be at least k edges basically, which means at least k plus 1 variables, at least k plus 1 nodes from beginning to end. Okay, so basically I want to claim that for a sufficiently long string, this path will have more variables down it than the total number of variables that G has. So G only has k variables, but this path needs to have more than k variables down. What does that mean? That means some variables are repeated twice. Okay, and in fact, if we look at the first repetition from the bottom, so starting from the bottom, we search for the first time the variable is repeated. This will happen within basically k variables of the bottom, because there's only k variables. So within, I guess, k plus 1 variables of the bottom, within depth k of the bottom, we will find two spots where there's a variable x, and then there's another variable x somewhere down this path in the derivation of w. So we are looking at w, right? But in the derivation of w, there's going to be an x that generates an x somewhere down as a descendant. Okay, so basically we're going to have this, basically we're going to have this, split into a bunch of junk, and at some point we'll have x. Okay, now we can have, so if we can look at the whole tree like this, then at some point we have x, and x will keep splitting down. So x will have its own subtree of only the things that this x becomes. Okay, so we have x, and it keeps splitting, and at some point it becomes x again. Okay, so we effectively, so let's draw these triangles. Let's draw a bigger diagram of these triangles. Basically, the diagram is like this. We start with a variable s. Okay, we generate some tree, which I'll just draw as a triangle. This is a giant tree. Okay, and then w is here at the bottom. So w is all the leaves here at the bottom. Whoops. Okay, so these are 0, 1, 0, 1, 1, 1. This is w here at the bottom. Okay, and this is just an abstraction of the tree. So I'm going to draw a triangle for a tree. And at some point, there's going to be x here down. So like, of course, this is going to be a bunch of forking things, but eventually we'll reach x. And x will have its own subtree of only the things it generates, which is like the subtriangle. And at some point, we will see x again. Okay, and this will, again, generate a tree. Okay. So our tree for w can be split into these three nested triangles. Okay, this one is headed by x, and this one is also headed by x, and then the top one is headed by s. If we call this, we can look at these strings here before, like in the first triangle before the second triangle, and then in the second triangle before the third, and then within the third triangle, and then again in the outside of the third, but still within the second, and finally outside of the second and still within the first. So we can look at these pieces of the strings, and this gives us a decomposition of w into 5 substrings: x, u, y, v, z. Okay. And what we know is that basically x can generate the string. Well, this is, hold on, this is little x, u, little y, v, little z. So x can generate, so this is capital X, the variable. Capital X, the variable, can basically generate u, y, v. Okay, because it can generate this top x. The top x can generate u, y, v, but also x can generate, the bottom x can generate y. Okay, so we know that the same variable can generate both u, y, v, and y. Okay, and basically we also know that, so let's write arrow star to mean can generate. So we know that s can generate little x, x, z. Okay, and then, so basically what we know is that s can eventually generate the string little x and then capital X, z. And we also know that x can generate u, x, v. Okay, and then we know that x can also generate y. Okay, so basically we can come to these conclusions. Okay, and also what we know is if we picked the deepest path in S, starting from S for the top tree to start with, and then if we pick the first two variables going from the bottom, climbing up from the bottom of the deepest path, and we look the first repeated variable, then the height here of the first repeated variable, we must have found it within like k plus 1 variables that we've seen, which basically means that the depth was k edges, k, which basically means that because it's a binary tree, that the width of this second triangle cannot be more than 2 to the k, which we called n. So basically what we know is that UYV is going to be at most n by the way we've constructed things. Okay, so the way we constructed things is that UYV will be at most length n. And this guarantee only works assuming that W is, assuming that W is at least length n. So assuming W is at least length n, then we get this decomposition, W equals x, u, y, v, z, such that the size of u, y, v is at most n. Okay, and also because x occurs twice and because kind of no path can become epsilon, then we know that it's not possible for both u and v to be empty because sort of no part of the tree can go to epsilon. So this x must be kind of a descendant of this x, which means there's another path where it wasn't a different child of this top x that does not lead to this bottom x. And that other path must become some non-empty string. So what we know is that u, v are not both empty. So in particular, the concatenation is not empty. Okay, and finally, we know these three things. Okay, and in particular, what these things can tell us is that we can apply the middle rule any number of times. So we can basically get S, we can get a derivation like this. S, we can turn it into, into this string, and then we can turn it into U. So we can do this, but then we can do this any number of times. So we can basically, actually, let me just draw it over here. So we can do this any number of times. And so we can get x u to the I, capital X v to the I, z, and then we can turn capital X into y. So we can get x u to the I, y v to the I. Oops. Okay, so, and we can do this for any I. So what we know is that basically the string x u to the I, y v to the I, z is going to be in our language A. It's going to be able to be generated from S for any I. So for all I and n. Okay, so this is the key property, and this is sort of the conclusion, the statement of the pumping lemma for context-free languages. So the statement of the pumping lemma is basically, for all CFLs, for all context-free languages A, okay, there exists pumping length n. So exists a number n, which is the pumping length, which is, you can think of this n as 2 to the k, where k is the number of variables in Chomsky normal form for context-free grammar for A in Chomsky normal form. Okay, so it's 2 to the power of the number of variables in a context-free grammar that's in Chomsky normal form for A. Okay, that's how you should interpret this n. It's roughly that. Sometimes it's smaller than that. It's never larger than that. Okay, there exists n such that for all w in A with the length of w being at least n. Okay, so if w is a string in A and the length of w is at least n, we have decomposition W equals X, U, Y, V, Z. Okay. With the following properties. One is that U, Y, V is at most n. So U and V are within n of each other. Two is that U and V are not both empty. So in particular, the concatenation is not empty. So either U is not empty or V is not empty. Okay. And then the most important point is that we can pump U and V together. So we can repeat U and V together any number of times. So X, U to the I, Y, V to the I, Z is in A for all I and N. Okay, so this is the pumping lemma for context-free languages. So to use the pumping lemma, we usually want to show that a language is not context-free. So we want to show that this lemma is not satisfied for that A. So we want to show that no matter what n might be the pumping length, there will be a string for which this property does not hold. So it's sort of like this game, right? So let's do an example. Let's show that the language A, which is this 0 to the n, 1 to the n, 2 to the n, is not CFL. So let's show that A is not CFL. So what we do is suppose it was. Then pumping lemma. Pumping lemma gives n. Okay, and then this is the n for which the pumping lemma should work, right? The pumping lemma implies there's some n for which the pumping lemma holds. The pumping lemma is basically this other player, and this other player hands us n. We are trying to show that the language does not satisfy the pumping lemma, so we're trying to get a contradiction. We're going to pick W. So our turn in the game. In our turn, we pick W. And we pick W in terms of n. So in our case, we will pick W equals 0 to the n, 1 to the n, 2 to the n. Okay, W can depend on n. And the lemma, it's the lemma's turn to play, and the lemma gives us the strings, this X, U, Y, V, Z. Okay, note that some authors, by the way, some authors write these strings in a different order, like U, V, X, Y, Z, where V and Y can be pumped together. But anyway, it's always the second and fourth strings that can be pumped together. That's the important part. The second and fourth strings are special. Okay, and then the first and last and middle strings are less special. Okay, so that's the thing to remember. Anyway, we're going to call it X, U, Y, V, Z. Okay, so the lemma gives us this composition, and it must satisfy the properties that U, V, Y is at most n, and U, Y, V, U, Y, V is most n, and U, V is not equal to epsilon. Okay, so it must satisfy these properties. And also that X, U, I, Y, V, I, Z is in A for all I. So we want to show that this can't possibly be true. So we want to get a contradiction. So we will note that basically this property implies that U and V, so because U and V are within n of each other, it's not possible for them to contain both a 0 and a 2, because the 0 and the 2 are further distance n from each other. So it's not possible for U and V to contain both a 0 and a 2. So either they don't contain a 0 or they don't contain a 2. And so if you look at X, U squared, Y, V squared, Z, well, the U and V are not empty, right? So they contain something, some non-zero numbers of zeros or ones or twos. But also they don't contain all of 0 and 1 and 2. Okay, they're missing either a 0 or they're missing a 2. And so X, U squared, Y, V squared, Z, either it has n zeros or it has n twos, because it's either the U and V didn't duplicate the 0 or didn't duplicate the 2. So either has n0 or has n2s, but it has length more than 3n. It's longer than the original string w. Okay, so it cannot have the form. It cannot have the form 0 to the m1 to the m2 to the m for any m, right? Because its total length is more than 3n, but one block is of length n. Okay, so it cannot have this form, so this is a contradiction. So because it cannot be an A, okay? And then therefore A is not context-free. Okay, so that's how you use the pumping lemma for context-free languages. It's pretty similar to the pumping lemma for regular languages, just kind of a bit more complicated because you're pumping 2 strings at once, and you're splitting your string into 5 pieces instead of into 3 pieces. Okay, and of course, just like for regular languages, sometimes we will show that a language is not context-free by using closure properties, and there's some examples of this in the notes. In particular, important closure property to use is that the intersection of a context-free language and a regular language is context-free. So that's a really nice property to use. Okay, so there's more examples of how to prove a language is not context-free in the notes, so I encourage you to check that out.